All right, so remember that we said if we had a cohomology spectral sequence, though it doesn't really matter, but I'll be grading it cohomologically. If we had some filtrations of the cohomology groups that we think we want, so FP plus first filtration of HN sits inside the FP filtration of HN, and so on, sits inside HN. And so we have one of these for filtrations for each N, not assuming any kind of finiteness here. And if we also have isomorphisms with our E infinity terms relating to the filtration quotients, then the spectral sequence, we said, converges strongly. I guess that's using Boardman's terminology or maybe McCleary, but not Weibel. Okay, and in fact, for this video, I'm mostly going to be following Boardman with a little bit of McCleary thrown in. So this converges strongly if, well, the filtration had to be nice. So what did we need? The filtration should be first exhaustive, and that didn't seem like such a big condition. Remember, that just meant that HN was really the union of all the filtered pieces. Okay, so typically that's what we mean by a filtration anyway. Hausdorff, well, that meant that our filtration quotients wouldn't be missing anything, so that's where we wanted the intersection of all the filtered pieces to vanish. And then finally, complete. And complete meant that we look at our HN, and this is actually the inverse limit of it mod each of the filtered pieces. Okay, and in fact, that was the completion of HN, which we talked about in the last video. And the whole point of this converging strongly, why do we say strongly? Well, the upshot here was that means that we can recover HN just by solving extension problems. Okay, well, that might not be easy, but let's say if we can solve all those extension problems. So, in other words, no weird lim 1 terms, no other problems. Just extension problems. Okay, and the upshot of what we talked about in the last video is really just that the spectral sequence doesn't see the difference between HN and its completion. So the spectral sequence can't tell the difference between HN and its completion, where we just take this limit. And remember, the completion had its own filtration, but that had the same filtration quotients. So what do I mean can't tell the difference? I mean that they're going to have the same associated graded terms, and so the same E infinity pages. And so you look at that E infinity page, and really what you're recovering is, if you could solve all the extension problems, then you can find the completion. But if your filtration of HN wasn't already complete, then maybe there's also some lim 1 terms to deal with or something like that. Okay, so now I want to get really into the nitty gritty of exact couples and see how this plays out with exact couples. Remember, all of our spectral sequences that we know come from a filtration of something. and or from an exact couple, and the filtration always somehow leads to an exact couple. So we might as well do this all in full generality for exact couples. So an exact couple looks like, well, we could really have any grading here, but I'm going to do this bi-graded because I want to have a particular example in mind. So I have these I maps, J maps, and K maps. I've got these bi-graded groups D and E, and I guess I'm calling it E1. So of course I could have my spectral sequence start in the E2 page or whatever. I'm just going to write it as E1. You could always re-index if you wanted. And the example I want to have in mind is the example, one of the examples I guess we've been looking at the whole time. So we have some filtered space, filtered CW complex with a cellular filtration, but not necessarily the CW filtration. And then we set as our E1PQ the cohomology of the filtration quotients, really the relative cohomology. And, well, okay, maybe let me not write P plus Q. Let me just write HN, but of course I mean N is P plus Q. I'm just trying to save myself some writing and also be able to kind of squint at this a little bit easier. So remember, this exact couple came from the fact that we have a long exact sequence. So there's my K map, maps to HN of XP. I'm in cohomology, so my I goes to HN of XP minus 1, and then I get my connecting homomorphism, which in this case is J, though in a lot of our examples it turned out to be K. If we do homology, it'll be K. But anyway, so that goes up a degree, and now I'm back to relative. And I won't write out the whole unraveled exact couple this time. But the point is, I want to sort of just think about an exact couple. I really want to think about this particular exact couple. So I could call this DPQ, right? And then my D star star is the direct sum of all of these things. And then I could call this, well, then it's going to end up being dp minus 1, but I still want the total degree to be n, so that ends up being q plus 1, so it's a little bit awkward. But the point here is that I preserves the total degree, by which I just mean n, right? So we could just think of changing one of those things. So McCleary says, let's look at dp star. So thinking of that for all the q's, and that's going to map to dp minus 1 star, right? I'm just saying, look at the homology of xp, it maps to the cohomology of xp maps to the cohomology of xp minus 1. Okay, so that's McCleary's notation. And then what does Boardman do? So Boardman says, well, let's just call that AP, and this AP minus 1. And I think both of them tend to use S, in fact, but I want to stick with our grading conventions. So in any case, if you look at that paper, you'll see lots of A's all over the place. That's what I'm going to call D, just those other bi-graded groups in our exact couple. And of course, they could be singly graded if we're doing the Bockstein spectral sequence or something like that. Okay, but now I want to get into the nitty-gritty. So remember that in this situation where we had a filtered space, maybe I should have written that. We had a filtered space, then we talked a little bit about the convergence, and we said that ZRPQ we would define to be all x in HP plus Q of XP comma XP minus 1, such that, well, what? So we said KX lands in the image of I to the R minus 1. Okay, so another way of saying that was that we can lift this thing at the diagram r minus 1 times, right? So we take x, we apply k of x, and it's the image of I to the r minus 1, so I could lift it up r minus 1 times, and then my differential was send that over, right? So the moral of the story is if I have something like that, I can define dr of x. Okay, maybe that's worth writing. So these were the things that we could define dr on. So now I want to be a little bit more general. I don't want to necessarily think about the cohomology of a space. I want to kind of do this for any exact couple, but just keep this example in mind. So let's take ZRP star to be, well, this is going to be K inverse applied to the image of I to the r minus 1. And that's a map from dp plus r comma star to dp plus 1 comma star. Okay, and that says exactly the same thing in this particular circumstance, but I can write that down for any exact couple. Okay, great. Let's do the same thing with BR. So we had BRPQ in our situation, we define that as J of Y landing in HP plus Q XP comma XP minus 1, such that Y was in the kernel of I to the r minus 1. And all I'm really trying to say is every exact couple could be unraveled. Let's just get rid of the cohomology terms here, and so we'll define BR. Well, again, I want to be kind of lazy about the second term because it turns out I don't really need it to talk about convergence. So I'll just take them all together. So B, P comma star. And we'll just take this to be J applied to things that are in the kernel of I to the r minus 1. Okay, and just to get our indices precise, that goes from dp star to dp minus r plus 1 comma star. Okay, and maybe I should have reminded you, scrolling back, so those things that were here that we could define our dr differential on, those were our cocycles, and then what were our co-boundaries? Those were things that came from at most r minus 1 places down, so at most r minus 1 steps down. Okay, and that's precisely what we've just defined. And notice that these agree in our particular situation. So now we've got to set up, well, our ER term. And as before, we'll take ERPQ to be ZRPQ mod BRPQ. And again, that notation is not universal, so some people make this ER plus 1. And we get a filtration where B1PQ is 0, the way we've defined it, and that sits inside B2PQ. And so on. So these are all nested. And then that sits inside BPQ infinity, sits inside ZPQ infinity. And then those are all nested, so Z2 sits inside Z1, and Z1 is just our E1PQ. Okay, I guess I said that I wasn't going to keep track of the Q's, and then here I am, but that's fine. We could replace all of those with stars, and everything that I wrote still holds. That's just sort of taking all of the Q's together, so that's no problem. And remember these infinity terms, what were those? So we said BPQ infinity should be the union of all the BRs. So they're nested, so that's really just the colimit. Of the BRs. And similarly, if I put a star there, and this sits inside ZPQ infinity, which is the intersection of all of the z's. And notice that that is an inverse limit. Okay, and one of the things that we've seen is that inverse limits are a little bit more complicated. There's a right-derived functor, right? The inverse limit is not exact. We get that right-derived functor lim1. And so that's going to come up for us as an issue when we get to talking about convergence. Okay, but for now, I'm still just defining these technical terms. All right, these are all as before, so nothing has changed yet except slightly generalizing to any exact couple. So we've got EPQ infinity. Well, what was that before? That was ZPQ infinity mod BPQ infinity. Okay, and notice that that's also the inverse limit over R of, well, since the BPQ infinity sits inside all of the Z's, that's really the inverse limit of ZR mod B infinity. Okay, so that comes with a lim1 term. And we won't need it right away, but this will come back later. So that lim1 well, I guess I could have copied that whole expression and written a 1. Still getting used to the tricks of the tablet. But anyway, this is what I think both McCleary and Boardman call RPQ infinity. Okay, so just R for right-derived functor. Okay, so that's going to come up for us as a kind of abstraction for convergence, but we'll have to get there. I just wanted to introduce it while we've got all the notation here right now. So a little bit of foreshadowing, I suppose. Okay, where are we? So we've got this exact couple. It's got our D groups and our E groups. And we want to be able to talk about convergence of the spectral sequence for this exact couple. And so to do that, we need to define a few more things. These did not come up in our previous examples, or at least not in this particular language. So one thing I want to do is, well, let's think about how we have this diagram that looks like dp star and I maps to dp minus 1 star and continue. Okay, so by abuse, I'm calling all of those I. And in our example right now that we're keeping in mind, that's the cohomology of the pth space and the p minus 1th space, right? Okay, and we can define d minus infinity comma star. This is going to be the colimit of the diagram. We can also define d infinity star. This is going to be the inverse limit of the diagram. And as usual, anytime we've got an inverse limit, then we also have a lim1. So let's go ahead and define that. While we're here, we've got r d infinity star, or as I said, if you look in Boardman, this is going to look like r a infinity. Then this is just the lim1 term for that same inverse limit. Okay, great. So what does that look like in our example? Well, here we've got d infinity star, so that's our inverse limit. When you're first playing with these, I think it's really easy to forget which one's the limit and which one's the co-limit. So I'll try to remind you. Well, in our particular example, each of those was the cohomology of the pth space. So it's the inverse limit of the cohomology of xp, right? And we take the inverse limit over p. So remember that we have this short exact sequence that has the inverse limit of the cohomology in it. So we had the cohomology of x surjects onto this inverse limit. This was due to Milnor. And then here we have this lim 1 term. Oh, I can't remember. I think this is -1. But it's not such a big deal. I just want to say there's a lim 1 term. Okay, so that really is going to be our RD infinity comma star -1, I guess. Anyway, okay, and so here, this is our d infinity star, and so we see that this is the thing that we're trying to cook up, right? We want the cohomology of x, so we're really interested in this inverse limit, and that's what we expect our spectral sequence should converge to. And so what is this d minus infinity term here doing? Well, in our case, that is the colimit. That's actually the definition. That's not our case yet. But that's the colimit of the dp stars. And so it's the cohomology of x minus 1. All I mean is that this filtration of x was bounded below. So if we keep going back, then eventually we get to x minus 1. That was the empty set. And so, whoa, sorry. So this is 0. Okay, so why would we even have this d minus infinity term if that's 0? Well, notice if we were doing homology, what would that look like? Well, really, I would have I goes from h star of x p, and that now, oops, I'm so used to writing cohomology. That maps to the homology of xp plus 1, right? And so that colimit would just be the colimit of the homologies of these pieces, and that would be our homology. Maybe let me write that down. So, okay, I'm going to try to be really careful about the infinity and minus infinity, but I can assure you that it's likely I'll make a mistake. So this is the colimit of the homology of all the filtered pieces, and colimits play well with homology, so this is the homology of x. Okay, so there's no need for a right-derived functor here. The colimit just is exact. And if we were in that situation, maybe we would want to reindex things or something, but in any case, that's the thing that we would be after. And so really what we're doing when we set this all up is being as general as possible. So I'm indexing everything as though it's cohomological, and I'm thinking about cohomology, but what I'm writing down here, we can write down exactly the same for a homological spectral sequence. So our exact couple can't really tell the difference. It's just a matter of indexing, right? And so all of this will hold in both cases. So that's why I want to make sure that I deal with both of these. Also, sometimes both things really come up. So spaces are particularly nice. In this, if we were doing the homology case, then when we look at the inverse limit, d infinity star, and we also look at the right-derived inverse limit, so that's our lim 1 term, then these would both be 0, right? Because that would be talking about the homology of x minus 1. Okay, so depending on the situation, we might have one as 0 or the other, and we see that coming up here in cohomology. Of course, in spectra can have negative cohomology groups And in fact, if we use other cohomology theories like K-theory, then of course we could have negative cohomology groups. So let me just mention for now that in spectra or other cohomology theories, they're possibly all non-zero. We don't necessarily get this kind of nice bounded situation. Okay, I think really, at least in that particular example, then really, I mean, in spectra that maybe are not connective or something like that. Okay, but in any case, often, and at least in our situations, I'll say have / want. Okay, this is really a nice case, but we do have it a lot of the time, which is that maybe just one of these is 0 or the other one is 0, either the limit or the colimit. And I think I just said those backwards. So colimit, or what I'm writing now, is the limit. Okay, so if one of those is 0, then we find ourselves in kind of a better situation for our convergence. But this video is getting a little bit long, so maybe let me stop there and we'll pick back up in the next one.